Welcome to Operating Systems Unit 10. Today we're going to talk about deadlocks. This is the first video in Unit. So we're going to talk about deadlocks in semaphores, priority inversion, and methods for handling deadlock. So a deadlock in a semaphore. Sometimes in a semaphore, if you take a look at this, process P0 is waiting, so is going to change the value of S to 0, but then P1 is going to change the value of Q to 0, and then P0 is going to be stuck waiting on Q, and P1 is going to be stuck waiting on S, so they're both waiting on each other, and they will not be able to signal because they're waiting on each other. And this can happen if semaphores are not set up very well, and so that you have to be very careful when you're using semaphores that they don't cause a deadlock. Just like in the dining philosophers in the last video, I did show that the dining philosopher semaphore solution could also end up with a deadlock. So another thing that can happen is starvation. You could have indefinite blocking. So a process may be suspended and waiting on a semaphore for a very long time, indefinitely, and it may not be in a deadlock, it's just starving because in order for it to get released, the process that needs to release it maybe has a very low priority, and so it's just starving the other process while it's sitting there being blocked. And there is a thing called priority inversion, which is when a lower priority process is holding a lock or a semaphore or a mutex or whatever needs to run a signal in order to allow the higher priority task to get past the wait or the lock or whatever it is. This concept of priority inversion doesn't mean solely a semaphore or a hardware solution. It just means that a higher priority task is waiting and a lower priority task is not getting scheduled to release it. So when that happens, your system could use a priority inversion protocol, and that would have the lower priority task temporarily inherit a higher priority in order to release and then go back to being its lowly priority again if that's the case. All right, so in your system you have a bunch of resources, and the processes share these resources, so the processes are going to request the resources, use the resources, and release the resources. So what we've talked about before in the request, you could use a semaphore to make a request, or you could use some help with the hardware or a lock or a mutex to make the request, or a monitor to make the request. Then use the resource, block all the other processes out from using that resource, and then release it. And what happens is, in a system, you can end up with a deadlock because the processes work together, and sometimes both processes, two or more processes, end up waiting on each other. So what does your system do when there's a deadlock? Well, first let's characterize what could cause a deadlock. If you have a situation like this where you have mutual exclusion, that means, for example, in this dining philosophers, only one of the philosophers can have a chopstick. It's a mutually exclusive item. You have hold and wait, so each of these philosophers is holding one chopstick while waiting for another chopstick. You have nothing in the code that says, no preemption, that says, well, you can only hold your chopstick for, say, 10 time units and then you have to release it. And you have a circular wait, which is very obvious here in the dining philosophers because they're in a circle, but the idea is that process 1 is waiting for process 2, who's waiting for process 3, who's waiting for process 1. Then there's a very good chance that you have a deadlock. It doesn't necessarily mean you have a deadlock, but if you have these 4 conditions, there's a very good chance that a deadlock could be occurring. So what do systems do to handle deadlock? Well, the first thing that a system can do is prevent or avoid deadlocks. And that means do not let a deadlock happen. Do everything it can to prevent deadlocks from happening or to avoid deadlocks from happening. The second thing systems will do is allow the system to enter a deadlock state and then detect that deadlock has occurred and recover from it. And the third thing that most systems do, which is very common, is just ignore the problem like an ostrich and pretend that deadlocks never occur. And this is used by most operating systems because unless it's a hard real-time or critical system, the amount of overhead involved in trying to prevent or avoid deadlocks is more, or recover from deadlocks is more work and on the system and more overhead than just ignoring it and leaving it up to the application programmers or the user of the system to restart. So let's talk about preventing and avoiding. The first thing we'll talk about is prevention. In order to prevent deadlock, what you do is you just do not allow all four of these conditions to happen at the same time. And there are some ways in which you can do that. So for example, in the dining philosophers, you could add preemption. You could say, oh, you can only have your chopstick for 10 time units, and if you're not able to pick up the other one, then you have to put it down. Another thing you could do in this traffic example that you can see here, no preemption doesn't make any sense here because you can't add preemption. You can't throw a truck or a car off the road, pick it up. So in this case, what you could do here is use traffic lights and not allow a process or a car to go through the intersection unless it's able to clear the intersection. So that way you would stop the hold and wait. It would not allow a car to hold the intersection and wait for the other one if it's not able to proceed through the intersection unless it can proceed all the way through. Mutual exclusion is kind of a hard one to prevent from happening because that's the whole point of the critical data, is that you want to block the other ones out. And circular wait is another way you could keep track of the resource types and not allow the circle to be closed. So in this section we talked about deadlocks and semaphores and how that could happen. We talked about priority inversion, and that's when a higher priority task is waiting on a lock that's held by a lower priority task. We talked about the system model and the request, use, release idea. We talked about deadlocks and methods for handling deadlocks, avoid or prevent, detect and recover, or ignore the problem. And then we elaborated on deadlock prevention. In the next video, we will talk about deadlock avoidance. Thank you.